Welcome to another video on Keeping Things Civil YouTube channel. This video will talk about example 3.9. This example is found in Fundamentals of Hydraulic Engineering System, page 77. When I started studying hydraulic engineering system, I found this example to be a little bit confusing, as the book doesn't really explain everything in details. So here we go. In figure 317, which is this figure, shows two sections of cast iron pipe. This is the first section and this is the second section, basically connected in series, that transport water from a reservoir and discharge it into air, basically, through a rotary valve at a location 100 meters below the water surface elevation. If the water temperature is 10 degrees Celsius and square-edged connections are used, what is the discharge? So basically he wants the discharge at this point. Now the discharge is of course denoted by Q. Q is equal to the velocity of the water times the cross-section area. The problem is that we don't have the velocity. Looking at this figure, and looking at this problem in general, the first thing that really comes to mind is the energy equation, which basically says that the energy at this point 1, should be equal to the energy at 2 plus whatever head losses had happened, during the transportation of water. So the energy at point 1 is P, which is the pressure divided by the unit weight of water, plus Z, which is the height, reference to a certain datum, plus the velocity squared divided by 2 times the gravity acceleration, should be equal to the pressure divided by the unit weight, plus Z, which is the height, plus the velocity squared divided by 2 times the gravity acceleration, plus the head loss, basically at point 2, of course. Now the pressure at point 1 is the atmospheric pressure, and the pressure at point 2 is also the atmospheric pressure. And since the liquid is the same, basically it's water, so we can take both of these terms. They could cancel each other, right? We take it to the other side with a negative, with a negative sign, and the net becomes a 0. Now, if we're using point 2 as a reference, then the Z at point 1 is 100. Yeah, and the velocity squared divided by 2 times the gravity acceleration at point 1 could be assumed to be 0, because this is a reservoir and the water won't be decreasing at a very fast rate, because this is a large volume of water. A small pipe connected at the bottom of it won't make much of a difference, and won't cause much of a rapid decrease in velocity, so we can assume it to be 0. Now the height Z at point 2 can be assumed to be 0. The velocity squared divided 2 times the gravity acceleration at point 2 is unknown. Basically we don't know what it is, and the head loss, we don't know how much head losses had happened. So 100 is equal to, using taking this equation back, 100 is equal to the velocity squared divided by 2g at point 2 plus the head loss. Okay, so the head losses that happened through the transition of water from point 1 to point 2, there are multiple head losses. We have the entrance head loss, which happened through the transition of water from this reservoir to this pipe, and then we have a friction head loss in the first pipe. We also have contraction head loss, because the water transitioned from a bigger pipe to a slightly smaller pipe, and we also have a friction head loss in the second pipe, and then we have a head loss at the exit because there's a valve. Now the entrance head loss formula is the head loss is equal to the KE, which is basically the entrance coefficient, the entrance head loss coefficient, times the velocity in the pipe squared divided by 2 times the gravity acceleration. Now the entrance head loss is 0.5. How do we find the entrance head loss? We observe this figure, and then we go to in the book it's actually referenced, if you look through the chapters, the entrance head loss is 0.5, because the water is, the pipe is like this, it's shaped like this, so the entrance head loss is 0.5. Okay, so 0.5 times V1 divided by 2 times the gravity acceleration. Since the equation, basically, now you can find that there's a problem here. This equation basically is written in terms of V2, which is the velocity at the second point, on point 2. But you're writing the head loss, or at least one term of the head losses, in terms of what? In terms of V1, which is the velocity here. So now we have two unknowns, and two unknowns with one equation can't really be solved. So in order to solve this equation, we have to use something, we need to write this in terms of V2 somehow, right? Since these two pipes are in series, the flow, which is the discharge in the first pipe, should always be equal to the discharge in the second pipe, meaning that the velocity in the first pipe times the cross-section area should be equal to the velocity in the second pipe times the cross-section area. The velocity in the first pipe then becomes A2 divided by A1 times the velocity in the second pipe, which then comes out to be 0.25 V2. Now, the head loss, then we can write the head loss. This is the head loss, at the entrance in units, or in terms, we can rewrite it in terms of V2. So the equation becomes, the head loss is 0.0312 velocity 2 squared divided by 2 times the gravity acceleration. Now, the pipe 1 friction head loss. So we're basically now talking about the friction head loss in the first pipe. The friction head loss is F1 times L over D times the velocity squared divided by 2G. This is also known as the Darcy-Weisbach equation. Now, F1, which is the friction coefficient, depends on the flow type. We either have laminar flow or turbulent flow. So, in this equation, all the terms are actually known. We have the length, we have the diameter, we have the velocity. So you don't have the velocity, and we don't have the gravity acceleration, but we can rewrite V1 in terms of V2, like similar to what we did in the previous step. So that will solve it. And the F1, we don't know how much friction, which is the friction coefficient. So the friction coefficient basically depends on the flow type, if we have laminar flow and if we have turbulent flow. If we have laminar flow, then the friction coefficient, the F1, basically depends on the Reynolds number and the E over D, which basically depends on the type of the pipe. If we have turbulent flow, then the friction factor will only depend on E over D. Now, in most pipes, basically experience a turbulent flow because the diameter is usually relatively small, moving from a reservoir. Therefore, it's assuming that the flow, it's usually assumed that the flow is turbulent. And either way, I don't have the Reynolds number, so I'm going to have to assume that the flow is turbulent. Of course, we're going to have to also rewrite V1 in terms of V2 using the previous equation, which still applies. V1 is equal to 0.25 V2. Now, the E over D, the E is the roughness, which can be found from the book, page 63. So you can go here and you can find the roughness height E for the problem mentions a cast iron pipe, so basically we have 0.26. Now this is in millimeters, so you have to pay attention. So 0.26 millimeters divided by 400 millimeters, which is 40 centimeters. So we get the E over D, and it comes out to be 0.0065. Assuming that we have turbulent flow, then the friction factor is 0.018. This is what we get from the Moody chart, also known the Moody diagram. If we take a look at the Moody diagram, we can see that when the E over D is 0.065, so basically somewhere in between both of these values. I'm going to assume it, along this line. When we have turbulent flow, of course, like you can see, complete turbulence of pipes, we can go straight, and you can see, like, when we have turbulent flow, it really doesn't matter what the Reynolds number is. We're just going straight, right? So if, for example, if the roughness is 0.015 and we have 5 times 10 to the power 7, it doesn't matter if we have 5 or we have 3 or we have 9 or we have 3 if we have 0.015. Now in this example we have 0.06, basically 0.3065, so something in between. We can go ahead and read it, so it's somewhere in here. Now we have one line, let's see, we have 1 line, 2 lines, 3 lines, 4 lines, and we have 5 between this one and this one, 0.05, basically 0.005, so we can say that each one is this one is 0.016, 0.017, 0.018, so we're going to assume that the value is 0.018. Okay, great, so we have F to be 0.018. Now the head loss using the equation can be found. 0.018 times the 1000 divided by 0.4 times 0.25 squared times the velocity, and you can see that we've substituted the V1 and rewritten the equation in terms of V2. Why did we do all this? Because the energy equation that we written in the start only has V2 as an unknown. So I can't use one equation with 2 unknowns. I need to use one unknown for one equation. So how we did this is we've said that these 2 pipes are in series, so therefore the flow is considered to be equal in both of these pipes. So we can find the head loss in the first pipe due to friction. Now we have contraction head loss, and the contraction head loss is equal to the Kc, which is the contraction coefficient, times the velocity squared divided by 2 times the gravity acceleration. Now the contraction coefficient, Kc, is usually needs to be given if we're talking, because it does depend on the velocity. But we can actually assume it, although it does depend on the velocity, we can assume it. So if we have, for example, in this example, we have the ratio to be, I guess, it became from 40 to 20, so the ratio is 0.5 basically. So it's in here. So it depends on the velocity, and we can be a little bit conservative. We can, guess the speed or the velocity, sorry, and we can find a value. So if you're in exam or if you have a homework, we can't really guess, so it's usually given to us. Because you can start guessing when you have experience and in pipes flow, then you can guess. But right now we can't guess because we're just students. Now the head loss due to friction in the second pipe formula is F times L over D, which is the length divided by the diameter, times the velocity in the second pipe square divided by 2 by the gravity acceleration. Now E over D, which is the this ratio, can be found also, like we did, 0.26 millimeters divided by 200 millimeters, which is of course 20 centimeters, we get 0.0013. Now the friction, basically the friction can be found similar to what we did. We assume turbulent flow, we go into the Moody chart or Moody diagram, and we find the friction, 0.021. Now we can get the head loss due to the friction in the second pipe, which is 0.021 times 1200 divided by 2 times the velocity squared, velocity 2 squared in the second pipe, velocity in the second pipe squared divided by 2 times the gravity acceleration, and finally we get 126. We also have a valve, and again we calculate the head loss basically, and the head loss comes out to be 10 times the velocity squared divided by 2 times the gravity acceleration. I think there's an issue here. This is not the KV, this is the head loss at the valve. I just fixed it. Great. So the head loss, the total head loss, is actually the sum of all of these head losses. We have entrance head loss, we have friction in the first pipe, we have contraction moving from the slightly larger diameter to the slightly smaller diameter. We have friction in the second pipe, and we also have an exit or a valve, basically. Friction, head loss. So if you want to look at the exit head loss, I think it's somewhere. This is the discharge coefficient, yes. So we can see, where is it? Where can I find it? Oh, okay, this is the valve coefficient. I found it. So here we have a rotary valve that's fully open. So we have a 10. That's the KV, the head loss to the valve, or the exit head loss. Sometimes we call it the exit head loss. So basically we have 100 minus the velocity squared divided by 2 times the gravity acceleration. This is the equation that we got from the energy equation, right? And then we have multiple things. All of these head losses actually depend on the velocity in the second pipe squared. So we can take that as the common term, and we can add all of these values that we get, right? So now we have 100 is equal to 140.17 velocity squared in the second pipe divided 2 by the gravity acceleration. Now, solving this equation, we get that the velocity in the second pipe is 3.74 meter per second. And now we can get the discharge, which is what we need in the question. It actually asks us to find the discharge. So what is the discharge? So we can now say that the discharge is the velocity times the cross-section area, and we can find the discharge. Now, before we find the discharge, we need to check that our check is actually correct, because we've assumed that the flow is turbulent flow, right? And this might not be the case. So we're going to have to check that. So we can create the Reynolds number for the first pipe and the Reynolds number in the second pipe. And the Reynolds number is the velocity times the diameter divided by the kinematic viscosity. And then we can check. So we checked the value, and the Reynolds number came out to be, for the first pipe, 2.6 times 10 to the power 5. And the E over D, we already have it. So going back to the Moody chart, we get that the friction is 0.018. So basically very close to the value, basically the same value that we've assumed for the first pipe, right? We've assumed it in the first pipe to be 0.018, so basically the same value. And for the second pipe, the F comes out to be 0.022. And we've assumed it to be 0.021. So a very small difference in results. We can either go back and recalculate everything, or we can just stick with this way. So basically now we can find the discharge. We've checked that our assumption is correct. The velocity in the second pipe is 3.74. Now we can multiply this by the cross-section area and find the discharge. So that's it. I mean, I found this example to be a little bit confusing if you're just starting out with hydraulic engineering systems. And it has a very large room for errors in calculations, because you're going to have to do a lot of calculations, and that can cause some error. So thank you for watching, and I hope this video helped you, and hit the like button and subscribe if you want me to maybe create another video.